Now we want to start talking about describing the pH of solutions that we prepare. We know that pH describes the acidity of a solution, and it describes really the concentration of hydroniums, right? It's the negative log of the concentration of hydroniums that in your solution. Those hydroniums are created by dissolving an acid, or an acid being present in the solution that donates a hydrogen to water to create the hydronium. And so the question would be, if I dissolve an acid into water, how much will it affect the pH? How many hydronium cations will be produced in this reaction? And really, the answer to that is, what side does the equilibrium favor? We know, we've just said that acids can produce hydroniums when they dissolve into water. But are they effective at producing hydroniums, or are they ineffective? And there's really two answers to this question. You could either have this reaction above with a situation, you could choose an acid such that the equilibrium is product favored, your K would be greater than 1. And so your reaction would go to completion, right? Your reaction goes to completion. You put some acid into water and it makes a lot of hydronium. So strong acids are acids that are effective at changing the pH of a solution. You put a little bit of acid into the water, all of it reacts with the water to produce hydronium. Weak acids are not effective. You could dissolve the weak acid into water. It can react with water to produce hydroniums, but for the most part, it's a reactant favored process. You mostly just have reactants. You don't produce a lot of hydroniums, so weak acids are ineffective at changing the pH. So we're going to use this designation, strong versus weak. An important thing to remember, this strong versus weak designation, the only thing it applies to is this reaction of an acid with water. Strong acids are very effective at changing the pH of water. Weak acids, less effective at changing the pH of water. There's no safety consideration. Strong acids aren't more dangerous than weak acids. They're not better at doing, they are better at doing chemistry in general, but weak acids can still be acids and can still cause problems, still have the same sort of safety risks we would want to be mindful of. It is only describing the reaction with water and the effectiveness at changing pH. Strong acids, effective at changing pH. Weak acids, not so much. And so when we are looking at, the solution level, if these strong acids are effective at changing the pH, because when those strong acid molecules, like for example, HCl, dissolve into water, they fully react, they fully process. This diagram is showing H pluses, kind of the old-timey description of acids, but we know those H pluses would attach to a water to produce hydronium. But importantly, that reaction of the HCl reacting with water goes to completion. There are no reactants left in solution, which would be unreacted acid molecules. A weak acid, for example, H2CO3, when this dissolves into water, it will not fully change. A lot of those acid molecules just stay acid molecules. Some of them do donate an H plus that would attach onto a water molecule and create hydronium, but a lot of them don't. So these weak acids are less effective, right? When we talk about effectiveness, what percentage of those acid molecules create hydronium? For strong acid, it's 100%. For weak acids, it'd be less than 100%, generally quite a bit less. So strong acids react completely with water. You will note we're using a single arrow to describe the reaction of a strong acid with water. So HA is just my generic acid. It donates the H plus, leaving A minus, and then you have the hydronium left over. So there are 6 strong acids that we're going to use: hydrochloric acid, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. So all of those are going to be strong acids. You don't need to necessarily memorize these as strong acids. You can always use just this list of 6. There are other ones that exist out there that are a little more radical, but these 6 that we're looking at, these are the ones that I would expect you to know as being strong acids and that we will use. These are also the ones most frequently used in lab, in a lab setting, and that's why we would use them. But when we're dealing with this process, whenever we're dealing with strong acids reacting with water, because we don't need to worry about an equilibrium description, we can use a full stoichiometry description. Whatever acid molecules you start with, right? 1 mole of acid molecules, produces exactly 1 mole of hydroniums when it dissolves. So you can use that stoichiometry. You don't need to worry about an ice table or anything like that. And so this initial concentration, this kind of nominal concentration, whatever you think you've made your concentration of acids, acid molecules in the solution, importantly, they all do react, but that concentration is going to be equal to the equilibrium concentration once the reaction is done. I've written it as equilibrium, but that's just when the reaction is done, which in this case would be all products are left, or very, very few reactant molecules. Let's look at an example. What is the pH of a 0.05 molar solution of nitric acid? So this is what we want to be able to do. We have our solution that we've prepared, 0.05 molar solution of nitric acid. We want to be able to characterize that solution by knowing what the pH is. All right, so what is the pH of a 0.05 molar solution of nitric acid? Okay, so when we want pH, we want to be mindful that pH has an equation. So pH is equal to negative log of the concentration of hydronium. So pH is our shorthand for acidity that describes the actual chemical picture at the molecular level. So what we want to think about is, where are those hydroniums coming from, right? What is causing hydroniums? Is it the equilibrium description of, just autoionization of water we've seen previously, or in this case, am I adding an acid? And so I'm adding something to the solution that's going to unbalance it, and I want to see how that shakes out. And so I have nitric acid here. So I'm just given the name. Acids have names that we can look up, or we may just learn. Nitric acid is HNO3. So nitric acid is HNO3. And one of the important things about looking up that acid is we can see that nitric acid is strong. What it means for nitric acid to be strong is that when I have this reaction, I know that the HNO3 aqueous, it dissolves in water. It reacts with water as an acid, meaning it donates this H over here to the water, becoming NO3 minus aqueous plus H3O plus aqueous. And so what we cared about was the concentration of hydroniums. Here is where they are. So the hydroniums are created by the nitric acid dissolving into the water. And so the question is, well, how many? So how do I figure out, based on my starting amount and my starting concentration, how much do I have here? The thing is, because nitric acid is strong, the reaction goes to completion. And importantly, that means I can use stoichiometry. I don't need to worry about an ice table. I don't need to worry about doing anything like that. I know that however many moles of HNO3 is going to react completely and turn into product. So this is a balanced equation. There's a 1 in front of this. There's a 1 in front of that. So we can do our relationship, and we can see that we have 0.05 molar HNO3. What that means is that I have prepared a solution that is 0.05 moles of HNO3 per 1 liter of solution, right? So this is like the initial preparation. The reaction actually happens. I make 1 mole of H3O plus for every 1 mole of HNO3. So these just come from my reaction coefficients. I'm just doing stoichiometry here. But importantly, I'm saying based on my starting concentration, this is how I prepared my solution. What I tried to design the concentration of acid to be, it's going to just be equal to the same concentration of product. So I'm going to have 1 mole of H3O plus for every 1 liter of solution, telling me that the concentration of hydronium is equal to 0.05 molar. Only two spikes in this. So this is always true of a strong acid solution because strong acid solutions always react completely. It's always just stoichiometry. They always donate 1 H plus to water. So the concentration of the acid that you set up, whatever you designed the solution to be, is what the concentration of hydronium will be after it's in solution. And this reaction happens extremely fast. So basically, when you dissolve it in, boom, right away, that's what the solution looks like. You got nitrates and hydroniums floating around in there. That's not quite all of what we wanted. That does describe the acidity of the solution, but we want to take that and turn it into a pH. So we can plug it in. The pH is going to be the negative log of 0.05, which is equal to 1.3. So when we talk about strong acids like HNO3, when we dissolve them in water, so I have these HNO3 molecules, for example, right here, and when they are dissolved in water, all of them donate their hydrogen to water molecules to produce a hydronium. And so what that means is in the actual solution, there are no nitric acid molecules, or a very small handful. There is some reactant, but you say you have a handful of molecules. It's going to be entirely nitrate that's left over, the conjugate of the nitric acid that you started with. And so that's what you're going to have actually floating around in solutions. That's why we talk about it as being like a nominal solution. So your 0.05 molar HNO3, you don't actually have 0.05 moles of HNO3, you have 0.05 moles of the nitrate that's left over and the hydroniums that are actually in that solution. And so, it really is, when you talk about a solution of HNO3, you're really just describing how we make it. And that's what we talk about. You would call it, you wouldn't say it's a 0.1 molar nitrate and 0.1 molar hydronium solution. You would really call it a 0.1 molar nitric acid solution. So this is a nominal concentration, but when we talk about it, when we talk about what the solution is, that's useful. And it's just kind of going to be one of those things that it's just something we know as chemists, like we're smart, we know that that is a strong acid, which we just figure that out by looking it up on the list. We know it's a strong acid, and that tells us that it is, going to be fully reacted. You're going to have a bunch of hydroniums, actually the active kind of component of that. And again, it's fully stoichiometry, goes all the way to products. You can also describe bases in the same way as strong versus weak, where strong bases react via stoichiometry, or can be described by stoichiometry, where they fully react all the way to completion. All of your reactants turn into products, and then weak bases don't. And so strong bases are good, effective at changing the pH. Weak bases are less effective. The most common strong base that we're going to talk about is going to be a soluble metal hydroxides. So your group 1A and 2A metals, so the alkali metals and the alkaline earth metals on the periodic table, those metals paired with hydroxides. So for example, sodium hydroxide. Those two columns, the hydroxides, are soluble. And so what that means is when they dissolve, if it's soluble, that means dissolving it in water is a product favored equilibrium where you fully dissolve, right? Whatever amount of sodium hydroxide that you put into the solution, it does fully dissolve. And we can see this is kind of the same idea of talking about nominal concentration when we know that ionic compounds actually dissolve into their separate ions, but we still call it a 0.1 molar sodium hydroxide solution. Even though at the molecular level, there are sodium cations floating around separately from sodium hydroxide anions, we still call it a sodium hydroxide solution, even though it isn't actually, little bits of sodium hydroxide floating around. It's the separate ions. Participation 222, question 3. What is the pH of 0.01 molar KOH aqueous solution? This is the third question on participation 222, due Tuesday, February 22nd at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the pH of 0.01 molar potassium hydroxide aqueous solution? Yeah, that one's it. There's 3 questions on participation 222. You want to find all 3 of those questions, get them answered due Tuesday, February 22nd. First set of videos will also be covered on the midweek homework due Wednesday on CHEM 101. And then don't forget also determining case C, the lab, due Wednesday. That is about equilibrium. There's no acid base there. So pre-lab, technique comprehension, all that stuff, that is all just equilibrium. None of this acid-base stuff on there. Otherwise, second set of videos, weekly homework, post-lab due Sunday. If you have any questions, let me know. Otherwise, I'll see you in the answers to this. Welcome to week 7. Welcome to chapter 14. See you later this week.